Okay, this is the last or fifth slide in our colligative properties PowerPoint presentation. I'm going to get back to our visualizer. I keep clicking don't show this message, but the message keeps showing. Okay, so there's a lot going on this slide. So we're talking about not just freezing point and boiling point, but also osmotic pressure. So this also isn't a completely descriptive title. Somebody needs to fix that. Who did this work? Is me. Okay, so we're talking about colligative properties, so physical properties that change based on the amount of particles that are added to a solvent, but not their identity. So whether they're polar or nonpolar or ions, doesn't matter, it's just how many particles. Okay, so our equations are, our leading question is why does the city coat the roads with salt when it will ice? The reason they coat it with salt, usually table salt, but sometimes other salts, is because it lowers the freezing point. So it has to get even colder for the roads to be icy. The reason they use sand though, so sand is silicon dioxide, I equals 1. It doesn't break apart into ions. It's not an ionic compound. So it doesn't lower the freezing point as much. However, it doesn't destroy or rust out the undercarriage. So the problem with salting roads, and if you've lived in areas where the winters are pretty brutal and they do that, if you check out the undercarriage of your vehicle, it's usually pretty rusty. Okay, so let's talk about boiling point. Boiling point elevation. And then freezing point depression. So I'm going to write the formulas and then we're going to do a couple of examples. We also have osmotic pressure. Okay, so boiling point elevation, what's nice is these two equations will be pretty much the same. Okay, this is a difference in boiling point is equal to a boiling point elevation constant, and you look it up based on the solvent, and that's times the molality of the solute. Molality again because it's per kilogram of solvent on the bottom, and mass doesn't change with temperature. We don't use molarity because it has volume in it and that changes with temperature. Times I, the Van Hoff factor. Before I write the freezing point depression equation, I want to talk really quickly about what this means. This is not the new boiling point. This is the difference between the old boiling point or original boiling point of the pure solvent and the new higher boiling point of your solution. The difference, so it's going to be a positive number, and how you get your new boiling point is you have to add. So this value that you get, you have to add to the original boiling point or the boiling point of your solvent. And that would make sense if sometimes students get so focused on solving a problem that they don't stop and think, does this make sense? And I know sometimes you're rushed and like, oh, I don't have time for that. But it takes 5 seconds. Stop. Does this make sense? If my boiling point of water is 100 degrees C, and it's boiling point elevation, that means anything I add is going to have an increase. So if you solve for boiling point delta TB, if you solve for this equation, and you calculated a number of 3.2, your new boiling point can't be 3.2. That's almost freezing. It's 103.2. So you have to add the difference that you calculate from the equation. You have to go back and add that to your original boiling point. All right, so freezing point's very similar, only we have F for freezing instead of B for boiling. And the same thing, you have to actually subtract because this is depression. we actually subtract this number from the original freezing point, or the freezing point of the pure solvent, right? So if you calculate this and you get 6.5 degrees C and you're in water, the freezing point of water is 0 degrees C. This is freezing point depression. When you add things like salt or sand to the roads, it decreases the freezing point, meaning it's not going to freeze at 0. It has to get even colder to freeze. So you subtract. If you got 6.5, when you solve the equation and it's in water, you would have 0 minus 6.5. So your new freezing point would be negative 6.5 degrees C. I have a couple of specific examples. I didn't want to do a ton of examples here. We're going to do one. Oh, let me write osmotic pressure. This one is just from the ideal gas law. This is straight up PV equals nRT. The only thing we added was I, our ion factor. If we solve for pressure, we've got N divided by V. N divided by V is moles per volume. Hey, that's molarity. So pressure equals molarity times R times T, and then we add that ion factor because this is a colligative property. So this is, you'll also see it as like a giant pie. Hey, write equations in a way that makes sense to you. It doesn't have to look like the book or even our videos. You could write it in words. Whatever makes sense to you. If you have a giant pie and it takes you 10 minutes to figure out what that means, just write capital P or pressure or osmotic pressure. Use words that make sense to you. All right, so we're going to work through the boiling point example, and then we're going to work through the osmotic pressure example. So this video might be a little bit long. All right, so our boiling point example from the slide. What is the new boiling point? And sometimes it'll look like that. Prime just means different, like not the original. T sub B is the boiling temperature. All right, solution of 48.9 grams of sodium acetate, CH3CO2. That's acetate. It's a polyatomic ion. When you take acetic acid and you take away the acidic proton, you get its conjugate base called acetate. And sodium is just a spectator ion. Okay, so we have 48.9 grams of that compound, and we have the boiling point constant for water, 0.512. We're missing a little information, aren't we? Yeah. How do I know that? Let's look back at our equation. I'm going to put it down here. I've got this, okay? I can figure this out, but molality would be moles of sodium acetate. AC is just a shorthand for acetate, divided by kilograms, and if this is aqueous, kilograms of water. Huh. All right, so I'm going to add a little bit of information to this problem so that we can solve it. I'm going to say in 250 mils of water, and that the density is 0.997 grams per mil. All right. Sometimes that happens when I make up a problem on the spot. Okay, so I need, or put it in a slide. So I need to calculate what's the change in boiling point. I know my original boiling point is 100 degrees C for just water. So I'm going to find this difference. I need the moles of this compound divided by the kilograms of water. I need the boiling point constant, which I have right there, that's given. And then I need I, the ion factor. All right, so first I'm going to start with the ion factor. Acetate is a polyatomic ion, so this one actually breaks apart into 2 ions. So I equals 2. Sodium 1 sodium, 1 acetate. This is a polyatomic ion, so these don't break into, oops, sorry about that. These don't break into pieces. Polyatomic ions don't split apart into their atoms. All right, so I is 2, Kb I have. All right, so now let's look at moles and kilograms. Oh, I think I'm gonna start with kilograms. So I've got 250 mils. If I multiply that by my density, gram per mil, my milliliters cancel, and I'm going to get grams. I'm going to solve that in on the computer calculator in just a second. I'm going to look back to moles. If I have 48.9 grams of sodium acetate, I need to calculate how many grams are in 1 mole. All right, so I've got sodium, which is 23 grams. I've got 2 carbons, which is 12 plus 12 is 24 grams. So that's my sodium. That's 2 of my carbons. 3 times 1, those are my 3 hydrogens. And then 2 times 16 is 32 grams. Those are my 2 oxygens. I'm going to put oxy instead of just O because you'll think it's 20 and then you'll be like, that doesn't make any sense. Okay, so 35 plus 24 plus 23, 9, 12, 3, 4, 5, 6, 7, 8, 82. So this should be 82 grams. All right, so now I'm going to pop over to this scientific calculator on the computer. I know I really need to purchase my own handheld. Okay. And I definitely recommend buying a little calculator, just a scientific calculator. You don't want to have to use your phone. You might have to use that as your mobile hotspot if you're taking an online exam. Okay, so I'm going to do 48.9 divided by 82. 0.9 divided by 82. 0.596. I keep a couple of decimal places. I keep a handful. I don't worry about significant digits really until the very end. Okay, and then my other one I want to multiply out is 250 times the density, 0.997, 249.25. Yeah, it's always really close to 1. 249.25. Okay, so I have those values, and then I just want to plug it all in. So I'm going to write on the paper, go back to my visualizer. I'm going to write my pieces out, and I'll pop back over to the calculator and get a number. Okay, so I'm taking my moles and putting it here. I'm going to do a quick convert to kilograms. 1, 2, 3, boop. 0.24925 kilograms here, and then I'm going to plug in these moles here. Okay, so let's see, actually let me do this. Let's see what that looks like. So the difference in boiling point is going to be 0.596 moles divided by 0.24925 kilograms, so that's my molality, times my boiling point elevation constant, which for water is 0.512. I'm being a little lazy and leaving off my units. This is actually per molal. It's degrees C per molal. And then our ion factor is 2 because sodium acetate just splits apart into 2 ions when it dissolves. So this factor right here, this is going to double the difference in the boiling point, right? Sand would have an ion factor of 1, but sodium chloride, or in this case sodium acetate, has an ion factor of 2. That doubles. So the number of particles it dissolves into has a direct impact on the change in boiling point. That's a big deal. That's a big deal. Now it's not going to double the boiling point, it doubles the change in. So I'm going to pop over and multiply all this out. I'm going to put this over on our other screen and work this out. Okay, so 0.596 moles divided by 0.24925 kilograms. So that's my molality, times 0.512. This is the boiling point elevation constant for water. And then multiply that by our ion factor of 2. This is a really concentrated solution, and it still doesn't have a huge difference. Still doesn't have a huge difference for, it's not going to be like a 50-degree difference. It's going to be just a handful of degrees. Now, this is not my new boiling point. This is the change in boiling point. Do not forget this step. Very, very important. Normal boiling point is 100 degrees C, just for water, plain water. We have to add the delta TB to get the new, I'll say delta TB, or sorry, TB prime, not the delta, just regular new boiling point. Okay, so this is 2.45. So that means my new boiling point is 102.45 degrees C. Okay. I am going to go ahead and stop now. There's another example on the slide, but I have a separate video for that type of problem that's already done. And this one's getting pretty long, so I'm going to go ahead and stop here.